Welcome to the Explainer. Today, we're going to dive deep and play detective. We're using the evidence right in front of us to decode a storm. Not one in the sky, but a storm raging inside the human heart.
So let's just jump right in. We all hear about irregular heartbeats, right? But what if it wasn't just a skipped beat? What if it was a full-blown electrical hurricane raging inside your chest? Seriously, what would that even look like on a screen? Well, what we're talking about here is a condition called atrial fibrillation, or just AF for short. So your heart's upper chambers, the atria, they're supposed to be the pacemakers. But in AF, instead of this nice, steady signal, they just start firing off chaotically. It's not just an offbeat rhythm. It's a state of complete electrical anarchy. You know, the best way to really understand what that chaos looks like is to see what it isn't. We need to put it right next to order. So let's take a look at our first clue.
Okay, what you're looking at are two ECGs. They're basically just readouts of the heart's electrical activity. On the left, that's panel A. You're seeing the heart during AFib. Just look at the line between those big spikes. That's the baseline. See how it's all jagged and messy? It looks like static on an old TV. Now look over at panel B on the right. That's a healthy rhythm. The baseline is so clean, so flat. It's the perfect picture of an electrical storm versus a perfect calm.
And this is where the science puts a name to what our eyes are seeing. That electrical static in AF, the term for it is chaotic micro-oscillations. It's just a fancy way of saying constant, unstable electrical noise. The healthy heart, though, shows a restoration of atrial electrical silence. Between beats, the heart's upper chambers are quiet. They're silent, just like they should be. It's literally the difference between noise and silence.
So we can see the chaos with our own eyes. That's clear. But to really get it, we need to zoom in. We need to actually measure it. So let's begin the hunt for this instability. Okay, this graph is like putting that instability under a microscope. It's plotting the electrical baseline from one heartbeat to the very next. Now, that calm, pretty steady blue line down at the bottom, that's your normal rhythm. But that red line, wow, that's atrial fibrillation, and it is jumping all over the place. This shows us that the chaos isn't just some background fuzz, it's a wild storm happening in that tiny, tiny gap between every single beat.
I mean, the visual evidence is pretty compelling, isn't it? That red line is obviously way more erratic. But in science, seeing isn't always enough. We need to prove it. Can we actually lock this down with some cold, hard numbers?
And here we go. This is our proof. What we're looking at is a measurement called the coefficient of variation, or CV. The easiest way to think about it is it's a wobbliness score. It measures how inconsistent a signal is. So look at the graph on the right. The box for the normal rhythm has a really low CV. It's super stable. But the box on the left, for atrial fibrillation, the CV is way, way higher. The wobbliness is just off the charts. This isn't just something we think we see, it's a quantifiable fact.
And hey, you see those three little asterisks right there above the AF data? In science, that's not just for decoration. That, my friends, is the statistical smoking gun. It means the result is highly significant. It's telling us that the huge difference in instability we're measuring is absolutely real and not just some random chance.
Okay, so let's recap. We've got the visual proof, we've got the statistical smoking gun. So how do we tie it all together? Well, that brings us to the breakthrough, a really elegant model that explains everything we've just seen. It's called the Shor's Sign 2.
This model lays it all out like a perfect chain reaction. It all starts with the condition itself, atrial fibrillation. Okay? That leads to a state of continuous electrical activity. And because the atria are never quiet, you get a loss of that baseline silence. This then shows up visually as those chaotic micro-oscillations we saw in that very first ECG. And finally, those oscillations are exactly what you can measure as that high CV score. It's a straight line from the disease to the data.
So here's the crucial point. The Shor's Sign 2 isn't just some fancy name. It's the whole story. It's a model that perfectly connects the underlying electrical chaos of AF directly to a measurable statistical fingerprint of that chaos.
So, we've followed the clues, we've uncovered this electrical fingerprint. But what's the big deal? What does this all mean in the real world? Why does being able to see this storm so clearly actually matter?
Here's the big takeaway, and it's a fundamental shift in understanding. Atrial fibrillation is not just a heart that's a little out of sync. It is a heart that is in a state of profound and constant electrical instability. Even in the quiet moments between the main beats, that storm is still raging. And knowing this, it has huge implications.
First, it just gives us a much deeper, more accurate picture of the disease itself. It also hands doctors a real quantifiable marker, that CV value, to actually track this instability. This could totally pave the way for smarter diagnostics. And looking to the future, if you can precisely measure the electrical storm, you might just be able to develop treatments that are way better at calming it down. Which leaves us with one last, pretty mind-blowing thought. We've just figured out how to see and measure the heart's electrical noise. So what if that noise is actually the earliest possible warning sign? Could understanding this electrical static be the key to one day predicting or maybe even preventing these heart conditions long before they ever become a full-blown storm?